Hi, everybody. It's Professor Mitchell, continuing with Chapter 1 on functions and graphs. Today, we're going to talk about Section 1.5, which is more on slope. So a lot of this section, or maybe I should say some of it, will definitely be review. We're going to talk about finding slopes and equations of parallel and perpendicular lines, interpreting slope as a rate of change, and finding a function's average rate of change. So this is the part that I think is probably review. Remember that parallel lines have the same slope as long as they have a slope, which means they're not vertical, which is what this says here. If two non-vertical lines are parallel, then they have the same slope. And conversely, if two distinct non-vertical lines have the same slope, then they are parallel. Two distinct vertical lines, both with undefined slopes, are parallel. So for example, to write the equation of a line parallel to a given line, we're going to write the equation of the line passing through the point -2, 5, and parallel to the line whose equation is y equals 3x plus 1. So notice that this equation is written in slope-intercept form, which makes it really easy to find the slope. The slope is 3. So the line parallel, or a line parallel to that line, will also have a slope of 3. So now we'll use the point slope formula to write the equation of the parallel line. Here is the slope. Remember, the point slope formula is y minus y1 equals m times x minus x1. So we're filling in 3 for m, and we're filling in -2, 5 for x1 and y1. So when we distribute the 3, or I should say when we first rewrite this as x plus 2, and then distribute the 3, we get, oh, actually they left it in point slope form. All right, so that's fine. And of course, if you wanted to write this equation in slope-intercept form, you would distribute the 3 and then add 5 to both sides. All right, in the next example, we're going to look at perpendicular lines. Remember that, so I like to say that the way they explain this in this section is sort of the grown-up way. All right. So what they say is that if two non-vertical lines are perpendicular, then the product of their slopes is -1. So a different way that you might have heard this before is that the slopes are negative reciprocals, which is a term that I'm not super crazy about. What we mean by that is, for example, 6 and -1/6, -3/4 and +4/3. In other words, flip it over and change the sign, negative reciprocals. But the grown-up way of saying that is that the product of the slopes is -1. And conversely, if the product of the slopes of two lines is -1, then the lines are perpendicular. All right, and of course, a horizontal line having 0 slope is perpendicular to a vertical line having undefined slope. So in this example, they're just asking for the slope of the perpendicular line. If you wanted to write the equation of that line, you could start that off the way we did in the previous example. I'll say that again when we get there. They want us to find the slope of any line that is perpendicular to the line whose equation is x plus 3y minus 12 equals 0. This equation is not written in slope-intercept form. It's written in general form. So the best way to get the slope of this line is to write it in slope-intercept form. So we start with the given equation. We subtract x from both sides and add 12 to both sides. That's going to give us 3y equals -x plus 12. Then we divide everybody by 3. Maybe I should turn my pen on for this. Okay, so when you divide everybody by 3, of course, you're going to get a y there. Negative x over 3 is the same thing as negative 1/3 x. And of course, 12 divided by 3 is 4. So there's the equation of the given line in slope-intercept form. So the slope of that line is negative 1/3. So what would the slope of the perpendicular line be? It would be 3. The negative reciprocal or the opposite reciprocal of negative 1/3, flip it over, change the sign, would be positive 3 over 1, which is 3. And again, they only asked for the slope of this line. If they wanted the equation of the perpendicular line, first of all, they would have needed to give me more information, like a point on that line. And then I could use the point slope formula to write the equation of that line. So hopefully everything that we've looked at so far is review. What's coming up for the rest of this section may not be review, but it's pretty easy, I think. So let's have a look at that. Slope as rate of change. Actually, you've probably seen this before. Slope is defined as the ratio of the change in y to a corresponding change in x. It describes how fast y is changing with respect to x. For a linear function, slope may be interpreted as the rate of change of the dependent variable, which is often y, per unit change in the independent variable, which is usually x. So for example, in 1990, 9 million adult men in the United States lived alone. In 2008, 14.7 million adult men in the United States lived alone. Use this information to find the slope of the linear function representing adult men living alone in the United States. Express the slope correct to 2 decimal places and describe what it represents. So we're going to take the information that's given in the first 2 sentences and we're going to make that into a couple of ordered pairs. So the first ordered pair is going to be 1990, 9. So X is going to stand for the year, and Y is going to stand for the number of adult men in the United States living alone in millions. So that's why we're writing 9 instead of 9 million. And then the other ordered pair is going to be 2008, 14.7. So we want to find the slope of the line through those points. And of course, we're going to do that with the slope formula. Remember, that's the change in y over the change in x. And I always recommend label one of these x1, y1, label the other one x2, y2. That's going to give you 14.7 minus 9 divided by 2008 minus 1990, which is 5.7 divided by 18. And to 2 decimal places, that comes out to 0.32. So the number of men living alone increased at a rate of 0.32 million per year, which is kind of a funny way to say that. You wouldn't normally hear 0.32 million. That would mean 0.32 times 1 million, which is 320,000. So the number of men living alone is increasing at a rate of 320,000 men per year. The rate of change is 0.32 million men per year. So remember, men is the number of men in millions is Y, and the year is X. So Y with respect to X changes at a rate of 0.32. All right, that brings us to average rate of change. Let x1 comma f of x1 and x2 comma f of x2 be distinct points on the graph of a function f. The average rate of change of f from x1 to x2 is given by this formula, f of x2 minus f of x1 divided by x2 minus x1. And in a little bit here, I'm going to draw you a picture so you can really understand what that represents. First, let's do an example. They want us to find the average rate of change for f of x equals x cubed from x1 equals -2 to x2 equals 0. So using the formula, f of x2 minus f of x1 divided by x2 minus x1, replacing x1 with -2 and replacing x2 with 0, you get f of 0 minus f of -2 divided by 0 minus -2. Remember, f of x is x cubed, so that means f of 0 is 0 cubed, and f of -2 is -2 cubed. Of course, 0 minus -2 is 2. 0 cubed is 0, -2 cubed is -8. So this says 0 minus -8, which is 8. So the average rate of change is 8 divided by 2, which is 4. So let me switch over to the tablet. Just want to draw you a little picture of what that represents. Pretty soon you're going to be introduced, or I should say reintroduced, to the graph of f of x equals x cubed. Hopefully you saw that in your trig class. I'm pretty sure you definitely did if you took it with me. The graph of f of x equals x cubed looks something like this. So this average rate of change from -2 to 0, it actually just represents the slope of the line that connects these 2 points. Oops. And that line, you'll hear this when you get to your calculus class, is called a secant line. Okay. Kind of a sloppy picture, but hopefully you get the idea. All right. I think that might actually be it for 1.5. Let's just make sure. Yes, that's it for section 1.5. So we'll see you next time.